Okay, chapter 12, problem 21. We have this strut that has a hinge at this end. There's a block suspended down like this on this side. There's tension in the wire here. They give us different angles, theta and phi, and they want us to figure out what the tension is and the force on the hinge here. All right, force on the hinge. So let's look at a few things. First, what we're going to do is we're going to look at this strut, and it is in equilibrium. And so if we zoom in on the top, where we have these few angles, um, that angle, that angle is easy, right? It's theta. Here's theta. It's theta 90 minus theta. Okay. This angle, right? This angle right here, if you look at this whole angle here to the vertical is theta 90 minus phi, and this is 90 minus theta, then this angle here, this little one here, turns out to be theta minus phi. All right, so that gives us that angle, because what we're going to do is we're going to kind of rotate this picture, and we're going to talk in terms of forces perpendicular to the strut and forces parallel to the strut, and break everything down in terms of that. And that's going to be important in terms of sorting out what's up with the hinge and what's up with the strut. All right, so doing that, right, here's the strut here. The weight, right, the weight goes that way. This is the angle here is 90 minus theta, right, 90 minus theta. And so the weight times cosine of 90 minus theta is the force parallel, and the weight perpendicular is the weight times sine of 90 minus theta. Well, this really turns out to be weight times cosine of theta is the force this direction, and weight times sine of theta is the force that direction. Similarly, we've got the tension this way, and this angle is theta minus phi, right? So the tension times cosine of theta minus phi is that angle, and tension times sine of theta minus phi is that force, right? So we get the parallel force, we get the perpendicular force, and then down here we have at the hinge some perpendicular and some parallel force at the hinge. All right. And so I'm going to start by summing all the forces in X. I'm going to call them, the vertical forces. I'm going to call them the vertical forces. So it's going to be tension times the sine of theta minus phi, and it's going to be the weight times the cosine of theta. And then the force here from the hinge, which I'm going to take to be up in this perspective. All right, so sum of f sub x's equals 0, right? Or, pardon me, f sub y's equals 0. So we had up the force in y for the hinge, right? And we had up the tension times the sine of theta minus phi. And we had down the force down from the weight. How much is the weight? 225 kilograms. Kilograms times 9.8 meters per second squared is the weight times the cosine of theta. Okay, this has only, we know theta, we know phi. The only thing we don't know here, we don't know the horizontal force on the hinge, and we don't know T. All right, now the vertical force on the hinge is Fy. So we're going to take Fxh, right? So here the tension is negative because it's pointing back towards the hinge. Away from the hinge is positive, back towards the hinge is negative, and also the weight gives us a, all right, times sine of theta. No, equals 0. Whoa, where'd that go? All right. So now we have FH in y direction, FXH in the x direction. We have the tension. We have two equations. We have three unknowns. Okay. Now, sine of the sum of the torques. Sum of the torques have to be 0. All right, so none of the forces that are parallel to the strut cause any torque, right? Because the sine of the angle there is 0. Sine of 90 degrees is 0. So let's look at the torque about the hinge. That also takes out FYH because that's at the hinge, right? So the tension up, right? The component of the tension perpendicular to the hinge, or to the strut, right? All right, how far away is it? How big is this strut? Oh, and I've forgotten the mass of the strut. We'll have to stick that in just a second. Concrete block. There's no length to the strut. Okay, I'm just going to put in times L for the length, right? And then the weight is, the weight goes in at, all right, the weight is going to be negative because the weight is a clockwise rotation, right? And so it's going to be basically this term up here times L. All right, now the term I forgot the weight of the forgot the weight of the strut, which is going to be 45 kilos times 9.8 meters per second squared, right? Times, okay, so the strut weight points in the same direction as the block weight. So there, it just adds in like this for that equation. And then for this equation, again, it points in the same direction as the block weight. Okay, now also when it comes to the torque, it points in the same direction as the weight due to the torque, and weight as the block weight. However, its distance is half that, right? It's a uniform strut. It's 45 kilograms spread out over its whole length, and so the center of mass or the center of gravity for it is right in the middle, which means the torque due to that mass is right at the center of the strut. So we add in this L over 2 term. Okay, so this gives us how many equations? 1, 2, 3 equations. We have 1, 2, 3 unknowns. The length divides out of this equation, and I think at this point we are good to go. I'm going to start doing some calculation. So theta minus phi is 15 degrees equals cosine of radians of 15 equals sine of radians of 15. Okay, so cosine of 15 degrees, sine of 15 degrees, and then we have 45, which is theta. Cosine of radians 45, sine of radians 45, right? Okay. So let's start at the top and work that equation, then the second, and then the final. Actually, let's start with this third equation. All right, I'm going to divide out the L. L goes away. We have 0 equals t times sine of 15 degrees is 0.259. 0.259 minus, okay, so 225 times 9.8 is 2205 minus 2205 newtons times cosine 0.707, right, minus, now we have, this is 45 times 9.8 is 441 minus 441 newtons times 0.707 times 1/2. Okay, from this we can find the tension. We get the tension is, let's just start adding all those up, 2205 equals 2205 times 0.707 plus 441 times 0.707 divided by 2, 1715 newtons divided by 0.259. Right, so I added up all of this stuff. Now I'm dividing by that, and we get 1715 divided by 0.259 is 621 newtons. 6621 newtons. All right, that's the tension. Okay, now we want the horizontal and vertical components of the, all right, so the way I've formulated this, what I'm calling vertical is not vertical, and what I'm calling horizontal is not horizontal. So we have to solve first for these two, and then rotate back into the original frame, right? Because this is, I really should call this F perp, right? And I should call this F parallel. What's a we'll do that, right? So F perpendicular, force of the hinge, F parallel, force of the hinge, and so we'll get to what those are. Because now we have this, right? Now that we have this, there's nothing unknown in this equation, and there's nothing unknown in this equation other than the piece we're after. Okay, so the piece we're after is, let's see, F perp H equals, all right, so we have 2205 times 0.707 plus 441 times 0.707. So 1870, right? That's 1870. 1870 newtons minus the tension, which is 6621 newtons times the cosine of 15 degrees, sine of 15 degrees, pardon me. Okay, so I need 6621 times the sine of 15 degrees. Okay, that's 1713 or 1714, so 1871 minus 1714 is 157 newtons. Make that a 1. So 157 newtons is the force that the hinge is providing perpendicular to the strut. All right. Now we're taking this equation, we're solving it for the force the hinge is providing this parallel. Okay, so okay, the parallel component of the force to the strut is, all right, so this minus sign is going to propagate through on everything. We're talking about 6621 times the cosine of 15 degrees. Oh, 6621 times the cosine of 15 degrees plus the weight times the sine of 45 degrees plus the other weight times the sine of 45 degrees. And so 8266. 8266 newtons, right? So this term plus that term plus that term, 8266 newtons. Now we got to get back to the perpendicular and the parallel components and think about what they are. So this hinge, this strut, is at 45 degrees. My beautiful 45 there. Okay, so it's at 45 degrees, and F parallel is in that direction, and it's 8266, and F perpendicular is in that direction. It's only 157 newtons. So if we're going to really look at what is the horizontal component and the vertical component, well, the horizontal component is this times cosine of 40 degrees, right? Minus that times the cosine of 40 degrees, and the vertical component is that times the cosine of 40 degrees plus this one times the cosine of 45 degrees. Sine, cosine, doesn't matter. All the same at 45 degrees, right? So if we're looking for F horizontal, Fx, all right, so that is F perp H times cosine of 45 minus F parallel times cosine of 45. All right, so that's going to give us the x component or horizontal component of the force on the hinge. So we have 8266 times cosine of 45 degrees is that minus 157 times the cosine of 45 degrees, and so 5734 newtons. And then the vertical component, okay, Fy, right? Fy is just the sum of these two, but instead of the cosine, it's the sine, right? Sine. And instead of being minus here, it's plus. And this is also sine instead of cosine. Okay. All right. So the parallel to the the piece that's perpendicular to the arm going out, and the piece that's parallel to it. So we have here, it was cosine plus, so plus, I'll just change it a little bit, and we get 5956. 5956 newtons, right? And the math was easy because the cosine of 45 and the sine of 45 degrees are one and the same. Okay, so this is the component, horizontal component and the vertical component of the force at the hinge. We back up. The tension on the line is 6621. Okay, 6621. The weight. Let's just check the weight real quick, just for a 225 kilograms and 9.8. So the weight is 2205. All right. I believe that is it for Chapter 12, Problem 21.